So, good morning, students. Myself, Dr. Sandeep Patil, and from today we will start uh, a topic from your physical chemistry syllabus. That is phase equilibria. This is from your physical chemistry topic. It involves the syllabus includes gives phase rule. That means rule equation and explanation of terms involved in the phase equation, phase diagrams. It's types of equilibriums, then one component system, there is water system, sulfur system with explanation for polymorphism. Then two component systems involves eutectic systems like silver and lead system, that is desilverization of lead, freezing mixture like potassium iodide and water, formation of compound with congruent melting point is ferric chloride and water. Then in three component solid liquid system, we will see development of triangular phase diagram, this is acetic acid, chloroform and water system. So this is the syllabus for your topic, phase equilibria topic. What is expected from learning expected from this topic is understanding of phase rules, learning of one component, two component and three component systems, and respectively their phase diagrams of different systems like water system, sulfur, then eutectic systems, okay, like this with suitable like these examples. So first we will see what is what is phase diagram or what is phase rule, why it is required. Before that, we must know what is homogeneous system and heterogeneous system, or homogeneous phase and heterogeneous phases. In any system, each physically distinct and mechanically separable portion of the matter which is itself homogeneous, that is uniform, is called phase. Okay, and any system consisting of more than one phase is called as heterogeneous system. So one phase system is called as homogeneous, that is uniform system, and when two phases are formed in any system is called as heterogeneous system. For example, in case of water, its freezing point, at its freezing point we know that ice, water and water vapors are present. Okay, so that is it is made up of three phases and it's called a heterogeneous system. That means at a certain point water may be present as ice, as a liquid and as a vapor stage. There is what is called as three phases, that is ice have three phases: solid, liquid and gaseous. So it is called as heterogeneous system. So the effect of temperature, pressure and concentration on heterogeneous systems in equilibrium, that is at equilibrium, can be studied very conveniently with the help of phase rule, which is also known as Gibbs phase rule, as it was deduced thermodynamically by the American scientist Willard Gibbs. So in phase equilibria we will study uh, these systems like homogeneous or heterogeneous, whatever may be the systems, their nature or the effect of different parameters like temperature, pressure or composition on the equilibrium of that heterogeneous system, and for that purpose a phase rule can be applied. So what is phase rule? So Gibbs phase rule, uh, derived by the American scientist Willard Gibbs, based on some equation. He has derived one equation for the uh, convenient explanation of such heterogeneous systems. The Gibbs phase rule itself explains that it states that as the sum of the number of phases and the number of the degrees of freedom of any system exceeds the number of components by 2. Okay, so what it states that number of phases, that is sum of number of phases and number of degrees of freedom of any system, exceeds the number of component by 2. Okay, provided that the equilibrium between any number of phases is not affected by gravity or by electric or magnetic forces by or by surface action. So mathematically it is expressed as P plus F is equal to C plus T, or F is equal to C minus P plus 2. This is called as phase rule equation, in which P is number of phases, F is number of degrees of freedom, and C is the number of components. So what are the terms? We will see these terms involved in phase rule equations. Okay, So, what is phase? Phase is defined as any homogeneous, physically distinct, and mechanically separable part of a system which is separated from other parts of the system by definite bounding surfaces. So, simply, phase is nothing but physically and mechanically distinct part of a system. Okay, so for example, through examples we can understand this. Consider a system containing ice, water, and water vapors. Okay, that means there are three phases: solid, liquid, and gases, and they are distinct from each other. That is solid, liquid, and gases. Three phases, each phase is physically distinct, homogeneous, and there are definite boundaries between them. Okay, so ice is one phase, liquid water is another phase, and what vapors is third phase. So it is called as phase. All gases mix in all portions and will constitute only one phase. If we see the vapor, if we see in air, there are number of gases present in air, but we cannot separate them, okay, into different phases. That's why it is called as only one phase, because all the gases present in air are mixed in such a way that this becomes a homogeneous phase. That's why gases mixture is always one phase. If two liquids are miscible, they will form one phase. That means acetone plus water. Two miscible liquids will form one phase because they will be miscible into each other. If two liquids are immiscible, then they will form two phases. That is benzene water. When some organic solvent like benzene is mixed with water, as you have seen in organic spottings on separation of organic compounds, there in separating funnels we are preparing uh, two types of phases, that is aqueous phase and organic phases. That means organic molecules or solvent like benzene are not miscible with water, so clearly we can see two phases. Similarly, each solid constitute a separate phase, okay, except in case of solid solutions. Okay, even though two or three solids mix together, actually they are not mixed homogeneously as like we are observed in solutions or liquids, but solids we can separate them by some physical means. We can separate the solids, but as liquid mixtures like acetone and water, they are mixed in such a way that we cannot easily, that means in physical ways we cannot easily separate acetone and water. It needs some a distillation type uh, techniques. Okay, for solid, it is considered that solid constitutes a separate phase except in case of solid solutions. Okay, consider a system in which calcium carbonate is separated or decomposed into calcium oxide and carbon dioxide, in which calcium carbonate is in solid phase, calcium oxide is also in solid phase, but carbon dioxide in gaseous phase. That means there is actually three phases, two solid and one gaseous phase. Then next thing is components. The number of components is defined as the smallest number of independently variable constituents by means of which the composition of each phase participating in the state of equilibrium can be expressed directly or in the form of chemical equation. Okay, for example, in water system we have three phases. Okay, component is different thing. Okay, and phases are different thing. Phases are physically distinct part, but component is different. In water system we have three phases, that is ice, water, and vapors, that is solid, liquid, and gas. These three phases are different forms of the same chemical substance, that is H2O, which is the only component present. Hence it is one component system. Thus any system consisting of a single chemical individual is always one component system. Okay, again any salt and water will form a two component system. That is, if potassium iodide is dissolved in water, then there will be actually two component. They may be, if they are soluble, they may form a homogeneous phase, but components are two. There are four phases in the system, that is solid potassium iodide, solid ice, water, and water vapors. All these can be expressed by two individuals, that is potassium iodide and H2O. Okay, so another example, interesting example, let us consider the equilibrium system of decomposition between calcium carbonate. Okay, calcium carbonate decomposes calcium oxide and carbon dioxide. Okay, here the phases are three, it is calcium carbonate solid, calcium oxide solid, and uh, carbon dioxide as a gas. The constituents taking part in the system are also three. but the composition of each phase can be expressed in terms of any two of the constituents in the form of chemical equation. Okay, as like a mathematics, it is like a mathematics. When calcium oxide and if we select calcium oxide and carbon dioxide, then we can write this same equation with the help of only two components. You can see in this slide, is if we consider a phase and we have to describe this phase with only two components, that is calcium oxide and carbon dioxide. You can see here calcium carbonate is the phase. We can write this in only two component system, that is calcium oxide plus carbon dioxide. The combination of calcium oxide and carbon dioxide itself indicates that presence of a phase, that is calcium carbonate. Similarly, calcium oxide will be indicated by calcium oxide plus 0 carbon dioxide, and carbon dioxide will be indicated by 0 calcium oxide plus carbon dioxide. Similarly, if we select calcium carbonate and carbon dioxide in this way, calcium carbonate plus 0 CO2, then calcium oxide will be expressed as calcium carbonate minus CO2, and CO2 will be expressed as 0 calcium carbonate plus CO2. Similarly, if we take calcium carbonate and calcium oxide in this way, we can explain this system like calcium carbonate plus 0 calcium oxide, then calcium oxide will be indicated as 0 calcium carbonate, and carbon dioxide will be indicated by calcium carbonate minus calcium oxide. Hence, it is a two component system. Here, zero and negative quantities of components are used because zero or negative quantities of components are allowed to explain. Okay. Now, the last term is degree of freedom or variance. It is defined as the minimum number of variable factors like pressure, temperature, and concentration, which must be fixed or stated in order to define the system at equilibrium completely. Okay, so minimum number of factors like pressure, temperature, and concentration that can be used or we can use to state any system, any state of a system. So minimum, it is nothing but a minimum number of factors like pressure, temperature, and concentration. Just for example, for a gas we have the equation PV is equal to RT. As we know that if pressure and temperature are fixed, then volume will have one definite value. Okay, if we fix the pressure and the temperature, R is also constant, that means automatically we get the uh, value of volume. So that means if only we can state the value of pressure and temperature, automatically we get the value of volume. That means we need not to give the value of volume. Okay, hence degrees of freedom will be 2. And again, let us consider solubility of salt. That is, for example, sodium chloride. It dissolved in water. Here, the system consists of saturated solution of sodium chloride in contact with solid salt and a vapor, and is completely defined if we mention only temperature, because solubility depends on temperature only. Hence, system has 1 degree of freedom. Okay, for solubility purpose only, because the solubility depends on the temperature. That's why if we only mention the temperature, we will explain the solubility. Again, for ice and water, ice water water vapor state at a particular point, which is called a triple point, all the phases are in equilibrium with eq- equilibrium, and we no need to explain any factor. So we, based on that, we can describe the system as invariant or non-variant, that is 0 degree of freedom, univariant, bivariant, and trivariant according to number of degrees at 0, 1, 2, and 3. Okay, that is invariant, univariant, bivariant, and trivariant. This slide or this schematic diagram explains this degrees of freedom. Okay, as we know that the phase rule, P plus F is equal to C plus 2. That means degrees of freedom, we can get degree of freedom as C minus P plus 2. So if we consider three phases, that is in case of water system, that is ice, water, and the ice, water, and the vapors, then phases are 3, component is 1, and we will get the degrees of freedom as 0. If we add this, that is C is equal to 1, P is equal to 3, we will get free F as a 1, OF as a 0. Similarly, if two phases are present, then we will get degrees of freedom as 1. If we only one phase is present, then degrees of freedom will be 2. That means we need to need to state at least two number of factors, that is pressure or temperature. Okay. Similarly, in this case, when two phases are present of water system, we need to give at least one factor like pressure or temperature. Okay, so this is about the introduction of phase equilibrium.